Good day everyone, I am Ana Angeline Mitra from Geoleng 2201 and I am here to tackle the research about delineating leachate groundwater interaction at Yadi Dam site, Kano, using natural electromagnetic field detector and vertical electrical sounding. So for our agenda, we will discuss the highlights abstract, graphical abstract, introduction, location and geology of the study, theoretical backgrounds, figure, materials and methods, results and discussion, and the conclusion of our research. For our highlights, it says that VES and EM reveal the presence of leachate and infiltrated depth of aquifer. The depth of leachate-aquifer interaction in the dam site is 40 meters. The attenuated leachate did not penetrate the shallow layer of greater than 100 meters away from the dam site. VES is better suited to accurately demarcate the true subsurface geological units, and NEF detector is effective for determining the extent of leachate plumb. How do geophysics connected with our study? Geophysical investigations are mostly used for hydrogeological studies, mining, geotechnical investigations, and environmental surveys. Geophysical investigation of groundwater within the dam site is highly critical because of the extent of interaction between the leachate plumb or contaminated zone and aquifer zones could significantly reduce groundwater quality. The textural complexity and clay content of soils could change their electrical properties, thus reflecting inconsistent resistivity values using the resistivity method. So in our graphical abstract, you will see here the geoelectric sections from VES which we will be discussed later. And also, you will see here the VES curve which illustrates the correlation of low electrical potential difference and low resistivity that reveals the presence of leachate and the depth to which an aquifer can be infiltrated. For our introduction, open dumping and waste transfer in Kano have evolved into a facet of the local culture of land reclamation, including the infill of excavations, deforations, and gullies. Apparently, this practice represents a serious pollution hazard, decreases environmental quality, and is against the principle of sustainable development. Infiltration or rainfall and other sources of fluid into a dam site coupled with biodegradation of waste generate leachate that is high in suspended solids with varying inorganic and organic concentrations. In contrast, the resistivity method is able to delineate and decretize the subsurface into subunits, different resistive zones. This implies that VES is better suited for accurately defining the true subsurface geology, while the NEF detector is effective for determining the extent of leachate plumb. Based on this geophysical data, it can be used to evaluate the leachate plumb, depth, part of flow, and the level of contamination on the subsurface soil and groundwater aquifer from waste dam site, which may be predominantly household wastes. In this research, the 2D electromagnetic technique using PQWT groundwater detector and electrical resistivity method adopting the Schlumberger configuration were integrated to the map the presence of leachate, the depth, and the range of percolation from the study area. So in this picture, you will see the Gyadi Court Road in Tarauni, northwestern Nigeria. At this point, the basement complex rocks consist mostly igneous and metamorphic rocks with relative shallow weathered mantle that permits very limited groundwater content. The basement complex areas subsurface water levels varies between 6 and 25 meters depth and in some places may extend up to 50 meters, while in child formation, water table ranges from 20 to 50 meters. So, in this figure, you will see the geology map of the Kano State, which depicting the different lithologies and rock types it has in the study area. So within the study, in calculating the resistivity, it used the fundamental physical law, which is the Ohm's law, wherein the J is the current density, which is equals to the conductivity times the electrical field intensity. But with the assumption that the ground is homogeneous and isotropic, it transferred to the formula wherein the volts is equals to the current and the resistivity over the 4 pi radius. It also uses the Schlumberger array, which is one of the type of VES configuration. The Schlumberger configuration procedure is based on the fact that the current penetrates continuously deeper with the increasing separation of the current electrodes. The illustration of Schlumberger array for electrical resistivity data acquisition, the C and P denote the current and potential electrodes respectively, where P1 and P2 is the potential electrodes and the C1 and C2 are the current electrodes. The WT groundwater detector uses natural time variations of the Earth's magnetic and electric field to measure the electrical resistivity of the subsurface. Therefore, electric and magnetic field is given as the formula of F is equals to Q times E plus VXB. But when the EM waves are sent to the subsurface, where the electrical conductivity is not zero, therefore the propagation of magnetotelluric field obeys the Maxwell's equations. The material employed in this research are compass, global positioning system, measuring tapes, hammers, connecting cables and reels, an EM meter using PQWT model, ohm meter using SAS 1000 ABEM, thermometer, battery, and the solar panel to charge the battery, electrodes, and other geophysical kits for geophysical survey. The procedure adopted in this present study involves geophysical data acquisition and detailed data analysis. So at the first figure, it shows the PQWT electrode arrangement for NEF data acquisition, wherein the N and M indicate the two potential electrodes utilized for the survey, while on the other side, it shows the location of the Gyadi dam site during the data acquisition, showing a variety of refuse waste littering the entire vicinity. So next we have is the vertical electrical sounding, or the VES. So the VES in which Schlumberger configuration was adapted in this study to acquire the apparent resistivity using the ABEM thermometer, and 6 VES points were occupied at the same profiles of the detector at the dam site. So the depth of the current penetration is proportional to the spacing between the electrodes in homogeneous ground, and varying the electrode separation provides information about the formation of the ground. So in Schlumberger configuration, the inner potential electrodes, or the P1 and P2, were maintained relatively constant, while the outer electrodes, or the C1 and C2, were successively increased outwardly with respect to the mean point of the inner electrodes. At this point, you will see the 6 VES curve for the different detector profiles. So from VES1 to VES6, the points of convergence signals on the NEF frequency model signify a medium with low resistivity on the profile map. So therefore, the leachate infiltration is most active at the shallow aquifers due to close proximity to the site of organic matter decomposition. Where the decomposed organic matter leaches into the aquifer, it introduces toxic cations and anions into the aquifer, thus increasing its conductivity. So for our table 2, it shows the lithology interpretation of the subsurface geo-sounding parameters for each BES point, such as the number of the layers, resistivity values, thickness of layers, depth, lithology, and the curved types of the presented table. So the correlations of the BES points with the EM profiles is to improve the subsurface geological declination, of the study area. So, for our geoelectric sections, the VES curves for different detector profiles along with their J-sounding parameters. The curves are mostly bowl-shaped types, indicating a topsoil underlain by saturated clay layer or weathered basement, which in turn overlain by fresh basement. So the closely spaced contours varying gradients in the NEF curves indicating fracture, which would facilitate potential leachate percolation. Moreover, the points of the convergence signals on the NEF frequency model signify a medium with low resistivity on the profile map. So, to discuss more about the leachate-aquifer interaction, this study said that the leachate has infiltrated the aquifer in various parts of the study area. In the northern, southern, and western regions, leachate has penetrated to a depth of approximately 40 meters. In contrast, the western part of the study area exhibits leachate-aquifer interaction extending to the depths of about 70 meters. For the natural EM field detector findings, it identified conductive zones indicative of leachate presence. However, the method faced limitations due to its relatively low resolution, which may have led to overgeneralization and difficulty in precisely delineating varying geological units. For the VES findings, the VES method provided more detailed subsurface information, delineating and decriticizing the subsurface into subunits of different resistive zones. This approach offered a clearer understanding of the true subsurface geology, highlighting areas with low resistivity that corresponds to leachate contamination. So, in conclusion, this study provides valuable insights into the extent of leachate infiltration at the Gyadi Dam site and the effectiveness of geophysical methods in assessing groundwater contamination. The recommendations offered are crucial for ensuring the safety and sustainability of groundwater resources in the area. For the conclusion, given the extent of the leachate infiltration, the study advises that boreholes for potable groundwater exploitation should be sited more than 100 meters away from the dam site. This distance ensures that the leachate aquifers interaction has attenuated, reducing the risk of contamination. The findings underscore the importance of monitoring and managing leachate migrations from dam sites to protect groundwater resources. This study highlights the needs for effective waste management practices to prevent contamination and safeguard public health.
That concludes our discussion. Thank you!